Welcome to part 2 of electromagnetic spectrum. The last video we talked about understanding the energy of different light, and what happens is when we pass light through a gas cloud, and if it's full spectrum light, in other words all the colors of the rainbow, what happens is as it goes through, certain frequencies of light we found to be absent. And the light that happens to be absent depended on the type of gas that we actually were using. And so this top one is called an absorption spectrum. In other words, what light is absorbed as it passes through. Now, we can actually calculate the energy of that light, and that light has to do with what's happening in the atom. And we're going to get further into that as we go. On the other hand, if we excited the gas itself, what it did is it gave off the colors of light that were missing in the absorption spectrum. They actually were emitted. So the emission spectrum, this particular one is hydrogen here. And so what we're seeing is we see 2, 4, 5 wavelengths of light that are visible to our eyes. And we're actually able to calculate the energy for each one of these by understanding, like I put on the last video, E equals h nu. So the energy of that wavelength of light is equal to Planck's constant times the frequency of the light that's actually being given off. And so what Niels Bohr did was he started to look at these frequencies of light and equate it to what's actually happening inside the atom. So we want to jump to the next slide and start to look at what Bohr was thinking about. So when we look at the emission and absorption spectrum, what Bohr figured out was, he said, you know what, the electrons live in certain energy levels or certain quanta. And so if we have an electron in the first energy level, so you'll notice we have this atom here, and each one of the circles, the dotted circles, represents an energy level. That electrons can either exist in this energy level or the next energy level, but don't exist in between. And so the wavelengths of light that we saw on the emission spectrum earlier were caused because of electrons dropping from one location to another. And so what he came up with is the whole idea that if I have an electron right here, as it drops, it actually emits this red light. Now, to get it, its original location is in the second energy level. So what we have to do is push in some energy. So we put in a little bit of energy, whatever that energy might be, and it pushes the electron up to the second energy level. Now, an electron in an excited state does not like to be there. So what it'll do is it'll return, and in that return it gives off the same amount of energy that it was given to move up. Or in this particular case, we can measure that by the color of light that's being given off. The same thing here. The blue light that we saw, the light blue, actually had to do with a drop from the fourth energy level down, and the first purple was from the fifth, and so on. And so there's different drops give you different colors of light. So because it takes different energy for each one of those jumps, and if we think back to the photoelectric effect, different lights give us different energies. And so that's what we're seeing in this atom. And so Bohr came up with this idea that he said that the change in energy, or the change in this wave that's coming off, is equal to what's called the Rydberg constant times 1 over the energy level 1 squared minus 1 over the energy level 2, in other words, where it dropped to. And so what we're able to do is measure the light or the energy that was given off. Now, as we start to look at Bohr, so as we look at these wavelengths of light, what we have is we have a wavelength here, and we need to find the energy of that wave. So we know that we need this equation that says energy is equal to Planck's constant times frequency. Well, the problem is we have wavelength. So we also need this equation that says the speed of light is equal to the wavelength times frequency. We also have nanometers, so we have to convert it to meters. So we start out by converting to meters. So we convert this. And as we said earlier in the last video that there are 10 to the 9th nanometers in 1 meter. So this comes up to be 486.1 times 10 to the negative 9th meters. Okay, so that's the first step. Now we need to convert from meters into frequency. So we have our speed of light, 10 to the 8th meters per second, is equal to our, I'm going to convert this real quick into proper scientific notation. Hope that doesn't bother you guys. Minus 7th meters times the frequency. And now we got to get to frequency, so we have 3.00 times 10 to the 8th meters per second divided by 4.861 times 10 to the minus 7th meters will equal our frequency. And if we're able to pull up a calculator again, we can do that calculation very quickly. Okay, so we do 3E8 divided by 4.861 E negative 7, and we come up to be 6.170 times 10 to the positive 14 per second. So now all we have to do is take that into our other equation that we were playing with earlier and say that the energy is equal to, if we remember Planck's constant was 6.626 times 10 to the negative 34th joule times seconds times the frequency, I'll put an X in there for times 6.170 times 10 to the 14th per second. And if you notice, what's going to happen is our seconds are going to divide out and leave us just simply with joules. So we multiply these two things together again. So we get 6.626 E negative 34 times, I think we had 6.17, yeah. So 6.17 E to the negative, or actually this was positive 14, and we come up with 4.11 times 10 to the minus 19th. So we get 4.110 times 10 to the minus 19th joules. Okay, so that particular wavelength of light is going to give us that much energy. Doesn't seem like a lot, but if we have a lot of photons of light, a lot of these, we can add up to a lot more energy. So what happened was Niels Bohr was able to quantize. In other words, he gave these electrons quantity based on the light that we were observing, and he came up with a series of numbers called quantum numbers that we're going to talk in the next video, where the first one is n, simply means it's called the principal quantum number, but really it's what energy level are we in. And if we look at it in this atom to the right hand side here, when we start talking about the energy levels, are we in the first energy level? Are we in the second? Are we in the third? So n is going to be either 1, 2, 3, 4, and so on. So in the next video, we'll get into these quantum numbers and start to talk about how they affect us and what we know from those particular quantum numbers. So a couple things from this. Understand that the electromagnetic spectrum helped us figure out what's happening with the electrons inside the atom. Niels Bohr quantized those numbers so that we can learn more about that. So we'll look forward to the next video where we start to talk about the quantum numbers and start to learn a little bit about what's happening with the electrons inside the atom.